today's intro notes, ladies and gentlemen, we're going to go ahead and set up a new objective and some new command terms for the remainder of the semester before winter break begins. And what we're going to be looking at as a topic is projectile motion in two dimensions, except this time instead of looking at it from just this vantage point, which is an object being launched horizontally off of a height, we're going to be looking at this problem to the right, which examines what happens to an object as it is launched at an angle and comes down at that same angle. To start us off, we're going to go ahead and look at our objective. Objective number one is I will calculate the horizontal and vertical variables for a projectile launched at an angle, as well as the flight time, time to apogee, height of apogee, etc. So basically we'll be calculating a whole variety of information. Objective number two, I will draw a projectile launched at an angle with the known and determined variables. These two objectives will be our objectives until winter break and probably even beyond, because these are the two big main pieces of what we've been building up towards. There are three command terms we're going to be using for the remainder of the semester. To determine means to find the only possible answer. To calculate, find a numerical answer showing the relevant steps for solving. And draw, that means to create a diagram or picture that visually represents the data. We also may do some construction of graphs as well if we have time remaining. So let's go ahead and start looking at what does it mean for an object to be launched horizontal or launched at an angle instead of just horizontally. Alright, so here is an example of a problem that we looked at previously, which basically is just what happens when an object is launched horizontally off of a great height. And there are two things that we had to keep in mind. Number one, that we have to pretend horizontally that the object has been launched along what's called a gravity-free path. So basically, horizontally, gravity doesn't exist for that horizontal motion. And then vertically, what is happening to that object if it just dropped out of the cannon? It would have just dropped straight to the ground. What would that object have looked like as it was traveling? And then it was the combination of those two that led us to understand what that projectile motion was. Now, looking at an object that's been launched at an angle is slightly different, but it involves a lot of the same things that we've already looked at, which is there is a vertical and a horizontal component. So if we examine this object, you'll notice that it has this projectile motion path it seems to follow. And all of these seem to be at an angle to each other. Now, with each one of these, there is a horizontal component. So as the ball is traveling upwards, it's also traveling to the right as well. So horizontally, this ball is moving, or this projectile is moving. And then there's a vertical component as well. So as the ball is going to the right, it is also traveling upwards until it reaches its apogee, and then downwards after it's reached its apogee. So projectile motion at an angle still involves both angles and still involves vertical motion as well as horizontal motion. An example of this could be seen off to the right as well. So you can see the object is traveling along this black arrow, and the two red arrows identify that there is a little bit of vertical motion as well as horizontal motion as well. So some things we're going to examine today in the notes is just what does that mean individually. So let's take a look at this example of the two types of motion we would see. So I'm going to add some arrows. Actually, I'm going to add some arrows here to identify this is the angle of the movement of the ball until it hits the ground. So this angled motion is a component of both the vertical and the horizontal velocities. So, yes, the object is traveling at a velocity at an angle, but it's made up of some horizontal as well as some vertical movement as well. So, some things to keep in mind is that, and we're going to examine the horizontal first, is that you'll notice here that as the ball is moving away from the person who threw it, it still seems to have a consistent speed horizontally. So what we saw in the previous problems last week is that the horizontal speed never changes. And when we throw a ball up into the air and away from us, that also still exists. There is no change to the horizontal velocity. So all the velocity that goes into moving the ball away from the person who threw it, that velocity stays the same. So something to remind yourself is that even with angled launches, horizontal velocity still stays the same. And that's due to the fact that we still don't have any acceleration horizontally. So gravity doesn't work horizontally, so we ignore gravity and just say there's 0 meters per second every second of acceleration. Okay, so that's examining the horizontal velocities. You'll also notice something with the vertical velocities that's a little bit unique, which is that the starting vertical velocity seems to be equal to the ending vertical velocity. And that's due to this phenomenon of basically objects going up and coming down at the same speed. So something to keep in mind is that the vertical velocities are going to be equal to each other both at the start and at the end. So basically the speed that it goes up with is the speed it comes down with. And we'll notice that these two are the same, but they are opposite to each other. So notice that the initial vertical velocity is a positive, meaning it's going upwards, and the final vertical velocity is a negative, which means it's coming back down to the ground. And if we were to set up this problem in all the vertical and horizontal components, then what we would say is that the vertical initial velocity is 19.6 meters per second, and the vertical final velocity is negative 19.6 meters per second. So basically the starting vertical velocity is the same as the ending vertical velocity. And this is different from our problems last week because last week we began at apogee. So basically we're pretending that the object had begun at its highest point, and so we were saying that the initial vertical velocity was 0. Well, now the ball is leaving and coming back to the same place that it started. So this is more of an example of the problems we looked at about 3 weeks ago where we would launch an object straight up into the air and then it came down with the exact same speed. Okay, so that's going to be it for today's notes. We'll explain this a little bit more in class and start using these in our notes. Pick up with these notes tomorrow as well. What I'd like you to do is to prepare for your exam or your quiz, not your exam, your quiz tomorrow, which is going to be on horizontal motion. I'd like you to answer this problem. A projectile is launched from an air cannon horizontally from the top of a 92-meter high building with an initial velocity of 19.8 meters per second. Calculate the time it takes to hit the ground as well as the distance it landed away from the cliff. So this is very similar to, this is actually the type of problems we were working on last week. So what I'd like you to do is set up what are my vertical and horizontal components, and then what are the steps for me to solve this problem, and then I'm going to go ahead and solve for the time it takes to hit the ground as well as the horizontal distance it landed away from the cliff. After you've answered that, go ahead and answer if you want the projectile to travel further from that building, what variable needs to change and why. And so the same thing, take a look at what we did last week and see if you can answer that question. What variable controls how far the object will travel? What would allow you to change the distance that the object travels away from where it started? We'll go ahead and have a quiz tomorrow, and this problem should help prep you for that quiz.